Good afternoon, students. How are you? So, started with new semester. Okay, so welcome to Ekeeda. And today we are going to start with the initial, basics of theorems. So, this is one of the theorem that is strain energy method. So, we'll not be seeing theory part, but we'll be solving problems on it. Okay, but yes, we'll be seeing some concept of it. Okay, basic concept behind it. So, this deflection of beams using strain energy method. So, what is strain energy method? So, the whole concept, according to your, whole structural analysis subject and all the content, you can see it in Ekeeda app. So, if you install it and go to structural analysis section, structural analysis 1 and 2, so you can get the whole syllabus there. Okay. So, all in-depth concepts are clear over there with all the problems. So here we will be seeing what is strain energy. Okay, strain energy when we consider with respect to a beam or any other structure. So basically our topic today is deflection of beam using strain energy method. Now it's very interesting. Strain energy. Now you know with your second year background, the basic we know that whenever any body, okay, body means any member if you take, okay, suppose in this case we are considering any beam. So now this particular beam, when some load is applied on it, okay, so this is a beam, some loads are acting on it. This is study purpose. Practical purpose, if you want to see, now if you are listening to this class and if you are sitting on a chair or a table or in your bed, so whatever whatever that's member. So let's consider other example of this particular chair. So these two examples we have taken. Now a simple thing in civil engineering, what we see, it's about the load acting on it, and because of load, what is that particular, any load, if it is acting on a structure, it will go under some deformation. Some deformation will be there. But yes, when you sit on the chair will not break, right? If you sit on that, if you are sitting here, it will not break. Why it is not breaking? Any reason for that? It will not break because there is some internal resistance, right? Some internal resistance of what? What is that internal resistance? Or is it that you are not giving the full load on the chair, or some magic is happening? So what is that? Yes, that magic is there. That magic is there. That is in the material, and that magic is actually given by civil engineers. Okay, so whatever material is there, when load is acting, yes, load is transferred to the ground by the legs of that particular chair. Okay, so it will be transferred to the ground. But what happens when this particular base is there? So when you are sitting on it, so definitely there is some deformation which is very negligible. Why it is negligible? Because when load is acting on it, there is some internal resistance. Okay, there is some internal resistance. And we all know, especially from your strength of material, we know that internal resistance is nothing but stress. We know that internal resistance, we call it as stress. But what about strain then? Where does the strain comes? Because now we are studying strain energy method, right? So what is that strain energy? So the strain energy, it is related with the material. Okay, the material. So what is the straining effect? Okay, so a very good example of rubber, elastic rubber if you take, or even your eraser rubber if you take, just if it is a long, so if you just bend it little bit, okay, if this is your eraser, and if you try to stretch it, so this is, suppose a eraser example I am giving you, or even girls can take their hairband, that elastic one, or this eraser you can take. So if you bend it, okay, if you just try with your hand, try to bend it like this, So it will bend like this. Okay, the shape will be like this. Now when you release it, it will again go back to original position, right? It will go back to original position. So what is that property? That is a elasticity. We all know that, right? It is well known. Now there is definitely something happens with the material when you are stretching it. There is straining action happens inside, okay, inside the material. So when you consider such cases, a beam or a chair, so what is happening when some external load is acting on it? So there is some deformation, okay, there is some deformation of a beam. So some deformation, slight, it is very negligible, okay, just for the showing sake I am showing like this, but otherwise it's very negligible. Okay, some deformation always happen over there, and there are some changes also happen along the cross section. So when changes happen along the cross section, you have also studied it in your last semester, that is when we have studied about bending stress and shear stress, right? That is across the cross section we have studied. Now this deflection of how do we consider the deflection of beam using strain energy? So whenever this external load is acting on a beam, so we call it as, there is a term called work is done. Okay, we call that there is some work is done over there. And when there is work is done because of due to external load, due to external load, now this should be equal to the, because of this external load there is some internal resistance because of the straining of material. Okay, so there is internal resistance due to straining of material. Straining of material, that can also be said in the statement that it is stored in the form of energy. Okay, that is stored in the form of energy. And that we call it as strain energy. Now if you consider any material, okay, if you consider any material on which some loads are acting, some loads are acting on it. So let me just scroll. Okay, some material is there and some load it is acting on it, say P1, P2, P3. Now and it is supported at some support. Now because of this loading there is definitely some deformation as we have shown in our first part. Now when we consider any element over here, okay, when we consider some element and if we want to plot, okay, for this particular element which is having a length dx and area dA, okay, let's consider it is having some length dx and area dA, and we want to plot the curve of it. Okay, what is the relation of stress strain? So when you plot a stress strain curve for this particular member, so it will be, we can show it like this, a curve. Okay, now when we plot this is a stress versus strain, so stress versus strain curve. So in some textbook this strain is also given by E and the stress is also given as small p. Okay, so it's one and the same. Now when we want to see what is the stress strain relation, so at any small element at any point, if we consider it as, let's consider at some level, so let's consider that at some point at level I, if you consider, or whatever name we can give, so the small element, what is the stress over there? So we can plot it by, suppose this is some point we want to show, so then our curve will be, the region shown will be like this for that small element. Okay, the stress versus strain will be shown like this. Now this is strain in the small portion, and this is total strain. What is the total strain? So for this particular curve where we have plotted till whatever point, the maximum straining capacity and the maximum stress capacity. So that will be our, this is total strain and this is total stress. Okay, so when we do that, what is the stress at this particular level? So that is sigma I, sigma suffix I, and this will be sigma suffix the epsilon suffix I, the strain at that particular element. Then strain energy stored in the element, we show it, strain energy stored in particular element, we show it as 0 to that particular epsilon, and that is the stress at that particular level, that I, that element, and then the, what is the small change in strain and total volume. So this is actually area under stress strain curve, area under stress strain curve. So if we want to plot it, now this is load versus this is stress versus strain. Now if you want to plot similar curve for load versus deflection, okay, so it will be similar only, the same way we can plot the curve. So here also for particular element we can show load like this, and deflection like this. So the y-axis is load and the x-axis, that is deflection. So deflection we can show as a triangle. Okay, so in this particular case there is some change in length over here. Okay, that is delta I we can show, and the complete deflection, the final deflection, that is delta. So we can show that by this final delta, and the total load carrying capacity as this particular P. Now this is stress versus strain, this is load versus deflection curve. Okay, so here we were at this part, but I just wanted you to see the comparison. Okay, this is stress versus strain, stress versus strain, this is load versus deflection curve. So plot will be similar. How it will be similar? When you divide load by area, area of cross section, that will become stress, right? And a strain will be change in length by original length, so that will become strain. So that is this curve. Okay, and this is load versus deflection curve, the first curve. So here area under stress strain curve into that particular volume, that is our strain energy stored, strain energy stored in the element. So we can show this as when you see this particular diagram. So whenever this is a curve, you can see, if in case it is a straight line, okay, so if it is a straight line, if this curve is like this, then what is the strain energy in that case? And when it will be straight line, so whenever it is a linear, means it's showing a elastic behavior. So in that case strain energy is nothing but area of this particular triangle. Okay, it is nothing but area of the particular triangle. So we can write it as half into stress into strain into that volume. Okay, so same equation, strain energy we can show like this. Okay, so I don't want to go much into depth of this theory, okay, because it's already covered, but I just wanted you to understand what is the basic of it. Okay, so similarly when we consider the load, okay, in that case work done, we show work done. So work done also can be shown as integration of what is that load, total load at that particular element into deflection. And when that curve is linear, for load deflection also, when that curve is linear, then we get half into P into delta. Okay, so this is one equation and this is particular equation. So finally we have to remember what is strain energy. Strain energy is nothing but area under stress strain curve. So that is half into stress into strain into that particular volume. Okay, volume of that particular element. So that we have to consider. Then when we consider strain energy due to bending, strain energy due to bending, this is also already covered strain energy due to bending. So in this case, when we further go into this theory, so we get that strain energy due to bending is U equals to, if you remember, it is U equals to 0 to L m square by 2 EI. Okay, so this is also already explained in a, this is already covered in a, if you go to Ekeeda app, you can find the how it has come. Okay, now I think we should go for a problem. We can consider, we can solve one question. So let's see a question now based on this strain energy. So we'll go with a simple question first. So using strain energy method, we have to determine deflection. Okay, determine deflection of a cantilever beam of length L subjected to point load acting at the free end. So this is beam, cantilever beam of length L and load acting is P. Now we have to use this formula, okay, above formula. So if you see carefully this formula, what all the terms we have. So that is m is there, then 2EI. Okay, what is the m? M is a moment. So when you see this particular beam, it is having only one load, that is P load acting on it. Okay, so this load is there, so we can simply, we have to write a moment equation. How we are going to write a moment equation? So let's consider any section at a distance x from here. Okay, so moment equation will be m equals to load into perpendicular distance. So m equals to p into x. Okay, so that is moment equation. That's it. So once you get a moment equation, simply substitute into this equation and we will arrive at the, after some point, we will arrive at the final deflection. Okay, so with this equation, we will be getting what is the strain energy. So when m equals to px, so let's substitute it in this particular equation. So let's write down strain energy is equal to U is equal to 0 to L m square by 2 EI into dx. So this is equal to 0 to L, m is nothing but p into x by 2 EI dx equals to, just take out constant values outside. So p is some value, p by 2 EI, yeah, it is square, right? So p square it will become, and x square when we integrate it will become x cube by 3, and the limit is 0 to L. Okay, so then p square L cube by 6 EI. Okay, so this is a strain energy we got. Okay, therefore U is equal to p square L cube by 6 EI. So this one answer we got. So let's name it as A. Okay, so we got A. Now this is strain energy. Strain energy because of the whatever load is acting. Okay, that is strain energy formulation we got. Now what is the work done by this particular load? Okay, what is the work done? So work done by the load is given as is equal to half into P into delta. Okay, so where delta is deflection, and our problem, what it is asking us to calculate the deflection of the beam, okay, using strain energy method. So let's find out. So let's compare A and B. So equate A and B. So when you equate A and B, we'll get P square L cube by 6 EI is equal to half into P into delta. So cancel this. PP will get cancelled. So delta you will get it as PLQ by PLQ by 3EI. So this is a deflection, and you have to remember this always. What is the deflection for a cantilever beam when point load is acting at the free end? So what is the deflection? Okay, so it's always PLQ by 3EI for the specific condition. Okay. Okay, I see Madan asked some question. What is the difference between elongation and strain energy? Okay, Madan, are you there? Still there? Madan, are you there? So I can answer you. Vamshi Yadav, what is the diploma topic? What is the chapter you are talking about? Any specific topic? Okay, Madan, are you there? So that I can answer you. If you're online, I can answer you. Trigonometry. Okay, we have so Vamshi, we have I think trigonometry subjects are there on Ekeeda app. I think if you just browse through the app, definitely there will be some faculty who are teaching it. Okay, I can teach it as well, but the subjects given to me are regarding structure analysis. Otherwise, I don't mind taking it. But just browse through Ekeeda app, you will find it definitely. Okay. So I'm teaching for civil engineering. I'm teaching structure analysis 1 and 2. So Madan, I don't see you. Otherwise, I would like to answer your question. What is the difference between elongation and strain energy? Okay, Vamshi, I'll see if I can take that. Okay. Okay. So for this particular topic, so we have solved this particular question. Okay. Uh, so let's see. Uh, for this particular case only. Okay. For this particular case, now when this beam, if this particular cantilever beam, suppose if we take a beam, now here suppose let's say there is some load is acting, say 100 kilonewton load is acting, and this span is 10 meter. Okay, so in that case what will be the deflection, and E and I value are constant. There is possibility that you may get a question that yes, if some cross section is given, okay, so in that case we also have to calculate what is the I value if it is given. Okay, so suppose let's take an example where I section, a cross section is given as uh, here it is 0.2 meter, 0.3 meter, or mostly in exam you will get it as you know, 200 millimeter means 20 centimeter by 300 millimeter. So any unit can be given. So you have to follow the common unit. Okay. So in that case, you have to find out what is the I value, and E is also given most of the time. So if in that case it is given, so you have to find out what is I value over here. So for this rectangle, you know, I value formula is BD cube by 12. Okay. So that is the formula you have to use. So for this particular case, you have to simply substitute values. First you have to write what is P. P is 100 kilonewton over here. Length is 10 meter. Okay. And I value, if it is needed, we can write down. Okay. You can calculate. If someone is there, you can do the calculation. Vamshi, even mechanical group, it is available on the Ekeeda app. Okay. You can just go through Ekeeda app, install it, and then you will find mechanical group, or you can just inquire about it on the WhatsApp number is shown on the screen, right? So on that you will get the help. So here delta is equal to PL cube. So P is 100 kilonewton, L is 10 cube by 3 EI. So whatever value is given, so that will be your answer. Okay, when you do calculation, so that will be your deflection. Okay, deflection. So it will be because this 10 is in meter, I is also, we have to convert it into meter. So that same unit will be there, and then finally you will get some answer for deflection in meter. Okay. Okay, so this is one question. Then we can take one more question. So this question, I think we can take about a frame. Okay, so let's consider a problem on frame. So let's consider. So it is determine vertical deflection. Determine vertical deflection of point C as shown in figure. So we are considering a frame over here. So this is a frame. This is A, B, C. This is I. This is 2I. This is 4 meter. AB length is 4 meter and BC is 3 meter. Okay. So this is the data given. Yes, E value is also given. That is 200 kilonewton per millimeter square. And I value is already given as 30 into 10 to the power 6 millimeter is to 4. Okay. So what we have to find out deflection at point C. So just now we have seen a question where it was a cantilever, right? Now even for this particular frame, it's like a cantilever over here, and this is having a load of 1 kilonewton acting on it. Okay. Now what we'll do, let's draw a free body diagram. Okay, so how will be the free body diagram? What is free body diagram? So free body diagram will be such that we will break the frame. Okay, we will separate the members, and after separation we'll see, okay, because of this load, what is happening at this particular end, what is happening at other end. So let's see that. Okay, so let's separate this particular frame. So I'm drawing here only. This is free body diagram. Now just see here. So when 1 kilonewton load is acting over here, okay, so to balance, when you see this particular member BC, okay, this is BC. So to balance this, when one load is acting over here, now it is no more together, okay, because we are drawing a free body diagram. Then in that case, it has to be balanced. So what we'll do, when 1 kilonewton is acting over here, now just forget this. So we have to show that it is taken care by 1 kilonewton load over here. Okay. So we will draw 1 kilonewton over here. Now, because of this point load acting, it is creating some moment at this point. Okay, 1 into that length. Okay, so some moment is there. So this length is 3 meter. So what will be moment over here? 1 into 3 means load into perpendicular distance. So 3 kilonewton meter. So now it is making a anti-clockwise rotation. Okay, that is how the naturally beam is trying to go in a clockwise direction. Sorry, not anti-clockwise. It is making a clockwise rotation, right? So it is trying to push the beam down. So to oppose that, there has to be anti-clockwise movement and this in this direction. Okay. So what we will do, we will show a anti-clockwise movement of 3 kilonewton meter. 3 kilonewton means 1 into 3. Okay, 3 kilonewton meter. So this is anti-clockwise movement. Now, work is done for the BC member. Now let's go to AB. Okay, so let's see AB. Now again we have to see the relation between B. Okay, B. So for here B, now when it is anti-clockwise, okay, again to resist that, there has to be clockwise movement. So we are drawing a clockwise movement. We have to show clockwise movement. So that is 3 kilonewton meter. Then this 1 kilonewton is going up. So to neutralize that effect, there will be 1 kilonewton force at this end. Okay. Now again to balance this, when this is clockwise, so there will be 1 anti-clockwise 3 kilonewton meter, and there will be also this reaction. So this completes our free body diagram. This is free body diagram of the frame. So, like the first case we have studied, when we had a cantilever beam with one load acting, so we have taken any distance x and we have calculated moment. Okay, why we have done that? What is that we want to do? We want to calculate vertical deflection at point C. Okay, how do we going to do that? So we are actually going to find out what is strain energy, okay, for the whole frame, and then that strain energy we are going to compare with work done. Okay, so if you remember the previous problem formula, half into P into delta, so delta term comes here. So when we'll compare it, finally we'll get the final deflection. Okay, so to reach that, first we have to calculate what is the strain energy. Okay, so from this free body diagram we have seen here. So now we have to write down the bending moment expression. Okay, so now let's consider first part. Okay, portion BC. So for portion BC, what is the moment equation? Okay, so how we are going to write? So in this particular case, we are starting our calculation from C to B. Okay, so here origin will be C. Okay, and what are the limits? Limits are 0 to 3. So limits will be, we are going to consider 0 to 3. Okay, and what will be the moment equation if you consider any section at this point? Okay, so moment equation will be, m will be 1 into x. So 1x. Okay, that is our portion BC. Now let's see portion BA or AB. So for portion AB, our origin, in this case B we are considering. Okay, because A being fixed end, it's we should start with the free end always, it becomes easy. So portion AB, here our origin we are doing for the calculation, that is B. It's B, and the limits will be, what is the length of that AB? Limits will be 0 to 4. So we are starting from this end, so 0 to 4. So 0 to 4 I have written, and then moment equation will be, again this particular, because of the load there won't be any moment, right? So what is the moment over here? Net moment, if you see, it is only 3 kilonewton. Okay, so 3 answer we will write over here. That's it. Once we have written it, then we have to substitute in strain energy equation. So strain energy equation is first for the part of 0 to 3. Okay, because this is 3 length. So BC portion. For BC portion, it is m square by 2EI. M square by 2 EI, right? Then there will be other part 0 to 4. Now here you have to be careful because 2 EI, but here already 2I is there. So 2 into 2 EI. Okay. So that part we have to always remember. Okay. So m square and here dx. Now you substitute all the values over there. So it is 0 to 3. M square is how much? 1x. So it is nothing but 1x is nothing but x. So it is 2ei dx plus 0 to 4. Here m square for this it is nothing but 3 value. So it is 3 by 4ei dx. Now this 1 by 2ei we will keep it out. Okay, and x will become x square by 2ei. Sorry, ei already we have taken it out. X square by 2, 0 to 3. 0 to 3 plus 1 by 4 ei 3 into x. X is nothing but 0 to 4. Okay. So when you substitute the limits over here, so 1 by 2 ei. So this will become 3 square, that is 9 by 2. 3 oh sorry, this is it should become square right here, so it will become cube by 3. So there is small mistake. So it will become 27. And this will be 1 by 4 ei 3 into 4. So again this is also 3 square. So this will become 9. Okay, so 9 into 4. So when we solve this, okay, so we should arrive at this answer 13.5 by ei. So that is our strain energy. Okay, strain energy. Now let's see what is work done. Work done is equal to half into P into delta. So what is P here? P is 1 into delta, that is delta by 2. So let's equate. Okay, this is our equation number 1. This is equation number 2. So equate strain energy is equal to work done. So when we equate these two equations, we'll get the deflection. So that is 13.5 by EI is equal to delta by 2. So delta is equal to, this 2 will multiply here, so it will become 27 by EI. Okay, so are you there? Anyone is doing calculation? So when you substitute, so we are at the end of the problem now. When you substitute value of E and I, so delta is equal to 27. Now E value, just let's see what is the E value given. E value given as 200 kilonewton per millimeter square, and I is 30 into 10 to the power 6, right? So it is given like this, but what till now our calculation, it is in kilonewton, that is fine, but we have considered a meter. Okay, so accordingly we have to do the changes over there, because this is 200. So let me just write it here only. So when we multiply EI, E into I, okay, so 200 is there, 200 into 30 into 10 to the power 6, 10 to the power 6, and this is millimeter square, this is millimeter raised to 4. Okay, so we have to multiply by 10 to the power minus 6. Then we will arrive at 6000 kilonewton meter square. So we have to substitute this value over here. That is 6000 kilonewton meter square. So then we'll get delta is equal to, so this will be in meter. So delta will be 0.045 meter. So this is meter, in meter answer. So in millimeter we can write it as delta is equal to 4.5 millimeter. So that is the deflection value. Okay. So when there is a frame, so what we have to do, the steps we have to follow, that when frame is given, okay, and we have to, it's been asked to find out deflection at some point at free end. So that case, what we have done here, we have to simply find out what is the strain energy in each member. Okay. So we have to first calculate the moment, then we have to substitute that into strain energy equation. Once we get the strain energy equation, then we have to also write down work done equation, then equate strain energy and work done, and when you equate them both the expression, then we'll arrive at the deflection for that particular uh, point, okay, for that particular frame at that particular point. Okay, so students, any doubt, anything you have, you would like to ask any question? Okay, so that is for today. Thank you for listening. Thank you.